we will solve this problem. Again, axial deformation of a rod or truss, one-dimensional problem, and to keep matters simple, we will assume that member axis is aligned along with the x coordinate direction. The only thing that is different here, I mean, it is uniform cross section, axial rigidity being AE, length L, rho is the density, and the only thing that is different from what we had considered earlier is that the surface traction, you may consider it as a like skin friction in a pile driving problem, or even load supported by pile, I mean pile supporting the load of superstructure, that is also similar case. And in this case it is end bearing pile. If you do not have this rigid support here, then it would be free pile, purely friction pile. In this case it is end bearing as well as friction pile. So we need to solve this equation using finite elements, and we will go step by step. We will try to solve it, uh, not try, we will solve it uh, in different ways. Finite element, using finite element, but in different, several different ways. So let us first find the analytical solution for this. This is a problem for which the differential equation is very simple, and analytical solution can be computed very easily by simply uh, introducing the by simply integrating the differential equation, and that will allow us to compare finite element solutions against this benchmark solution, and that will also set a basis for what we can do for other finite elements for which, or for other situation in which the analytical solution is not available, and by comparing how the finite element solutions compare against the exact solution for this differential equation, analytical solution for this differential equation governing this problem, that will hold uh, lots of hints and suggestions how to identify. I mean, sometime a couple of lectures back, somebody had asked this question, uh, that how do we decide the size of the element in a finite element discretization. So that question actually triggered this lecture. I had planned to do this in yesterday's lecture, but yesterday was spent in discussion. So let us do that, and let us study the analytical solution of this, and we also study the solution of this problem by using finite elements, different ways how we can solve this problem using finite elements, and what is the effect of those differences in different uh, instances of finite element solution, and how to interpret the results, or how to read the results of a finite element solution. So let us first try to write the differential equation. So considering the free body diagram,
Sir, you are not audible.
I am not audible.
So now it is okay.
Okay.
Now you are audible, but what you said after interpret was not audible.
Okay, so my voice was lost for some time in between. You see, you mean?
Yes, sir.
Yes,
Yes,
sir.
sir. Even
The voice in the video as well.
Okay. Okay, audio capture is working fine. Okay, so anyway, what I meant to say was uh, we will try to solve this problem, simple one-dimensional rod problem, analytically first, and then solve this problem using finite element modeling, different types. We will develop different types of finite element models we will use to solve this problem, and then compare the finite element solutions against the benchmark of this analytical solution, and that will provide us the hints and suggestion how to interpret finite element solution in these situations where the exact or analytical solutions may not be available, and accordingly decide. I mean, the whole point, the reason why we are doing this is the question that was raised earlier, couple of lectures back, that how do we decide the size of finite element while discretizing the domain, while dividing the domain into different finite elements, how do we choose the size? So let us start working on that, and to start with that, we let us first work out the analytical solution for this problem. And to derive the analytical solution, we need to first find out what is the differential equation, governing differential equation of the problem. So for that, we draw the free body diagram representing all forces in the system, acting in the system. So this is the axial thrust, and this is the skin friction, length dx, and there would be I can say that's the fictitious inertia force, which would actually take care of the rate of change of momentum. So now if we establish the equilibrium of all forces, so we can just say net force acting on the differential element dx is minus dx because it is acting in the negative direction, q x dx, that is in the positive direction, plus t plus dt, and this should be equal to rho a dx multiplied by u double dot. So this is Newton's second law, law of momentum. Mass is time invariant, so rate of change of momentum is equal to mass times acceleration. So this leads us to the basic differential equation. Rate of change of axial thrust is equal to rho a del T u by del T square, and T axial thrust is of course equal to A times sigma axial stress multiplied by the area of cross section. Axial stress is equal to A times epsilon, right? So sigma xx epsilon xx, direct strain sigma xx is of course equal to Young's modulus multiplied by the direct strain epsilon xx, and that is equal to AE del u by del x. So that's the direct strain value, and we can substitute this in the differential equation. So this t can be substituted in this, and we will have del over del x AE del u by del x. Okay, this will also be partial because we are considering this time as a variable as well. And what is q? Qx is varying linearly from q0 at x is equal to 0 to 0 at x is equal to L. So this is equal to q naught by L multiplied by L minus x. You can develop it using equation of straight line. Y is equal to y1 plus y2 minus y1 divided by x2 minus x1 multiplied by x minus x1, and you will get this expression. So we can write this here, q naught by L multiplied by L minus x is equal to rho A del 2u by del t square. So that is in omega x ranging from 0 to L with the boundary conditions being u at x is equal to 0 and AE times the axial thrust at the free end is equal to this applied force point load Q. Right? So these are the boundary conditions. And for the time being, for the simplicity, to concentrate on just the finite element discretization aspects, we will ignore the time dependence for the for this problem.
Sir,
Yes.
in this case, why don't we need to consider that axial thrust as a function of t as well when we take t plus dt?
It is a function of t as well.
Then when we take dt, don't we need to consider dt dou t by dou x? We also need to consider dou t by dt as well, na?
No,
Or
this
not?
is variation with respect to x only. We are changing. I mean, this free body diagram. We are exploring the variation of all the forces across the infinitesimal length dx. Variation with respect to time holds for entire domain. That is a separate thing.
Okay.
Right? So these are all instantaneous values.
Oh, okay, got
So
it.
for each time instant t, these are the this is the picture snapshot.
Yeah, got it.
So we can say this is a snapshot at any particular time instant. Right? So neglecting time dependence, to, okay, just,
Sir,
yes,
sir, you said that we are considering any element at any particular instant of time.
we are
It means that
considering,
that element every
yes,
week
this
at a
one,
particular
LBD,
instant of time.
yes, 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 that's right.
But all the parameters are varying with distance x and time also.
Yes,
Then why we are neglecting time dependence?
we are not neglecting time dependence, we are taking the snapshot at any instant of time. So these are the forces, these are the components that are acting. Now the value of these components may keep changing with time, right? So t will be some value at time t1, it will have some other value at time t2. Q can have some value at time t1, it will have some other value at time t2. Right? If it is also, if the skin friction is also time dependent, although we do not see the skin friction to be time dependent phenomena as far as uh, the time scales that we are dealing with, right? But acceleration can of course be time dependent. So you have some acceleration at time t1, you may have some other acceleration value at time t2, right? So these are all the forces we consider acting on this element of differential element that hold this particular differential element in equilibrium at any instant of time. So the whole idea is that of the whole idea of using this fictitious inertia force concept is that you can extend the concept of static equilibrium of forces acting on a body to the dynamic situation. Otherwise, you need to look at this second law of Newton's laws of motion, law of momentum. At any instant of time, what is the net force acting on the body? So this is the net force acting on the body at any time instant. Individually, each of these values may be changing with time, but any particular instant of time, this is the net force that is acting. And this net force should be equal to rate of change of momentum of the body at that particular time. And individually, all of them may evolve in time.
Sir, then you mean that we are going to analyze different element at different instant of time, and then later on we will going to club them.
At the moment, we do not consider time variation at all. That's what I am saying here, neglecting time dependence. So we are ignoring any time dependent variation. We are just assuming that we are dealing with a static problem. So this right hand side will be 0.
For
And
whole system.
pardon?
Sir, for complete system, not for a particular element, for a
For the
complete system.
right at the moment we are only looking at this problem. We are not yet uh, discussing finite element so far. We have not even started with finite element anywhere so far. Right? It is a simple analytical model of a rod of length L, uniform axial rigidity, subjected to some surface traction and some end load. So this is the governing differential equation and associated boundary condition. So if I neglect the time dependence, the governing differential equation becomes partial derivative will now become uh, total derivative